Hello, everyone. If you're following along in the textbook, this will be a little out of order. This video is on chapter 23, which will be the birth of the universe, the Big Bang. How did stuff happen? The next video will be backwards on chapter 22, which nominally in the text is dark matter and dark energy. But in those two things are the fate of the universe. What is the dynamical path that the universe will take? How will it evolve? What will happen to all the stuff that's in it? And so it makes more sense to start at the beginning and then go to the end. So this is the birth of the universe. Now, what I have here is a very interesting picture. I will get into it in a bit. You've probably seen this before. If you have an interest in astronomy, you've seen it before or seen something like it. And I'll show several of these. So, just without even considering the physics, there is basically two possible histories. One is what's called the steady state universe, and the other is the Big Bang. One says there's a beginning, the Big Bang, and the other says no, there ain't. And they both have had their proponents in time. I'll tell you a little bit of the history of it. Here is Um, if you go look up a guy called Fred Hoyle, he's the guy that staunchly promoted the steady state universe. Um, and I'll mention this for a moment. He was an atheist. Um, and part of his reasoning had to have been focused by the not looking for a creation moment. Just so you're aware. Um, the other main theory, the Big Bang, the initial sort of impetus to it is was a guy called Georges Lemaitre, who was a Catholic priest, and he was in particular he was a Jesuit and was an astronomer, a proper astronomer. He was looking for a moment of creation, a first instant, and they were in different generations. Right? Is Lemaitre was a contemporary of Einstein and talked to him a bit. Einstein, uh, if you go and study in detail what he was doing, he came up with a set of equations that describe how space looks. And we talked about gravity and curvature and everything. And the goal was kind of to find a reasonable description of the entire universe, like an approximate description. And he came up with a steady state model. Um, and his first set of theories wasn't exactly useful in the sense of people looked at him as like, well, no, this describes the universe now, but it will evolve away from what we're seeing. Is it allows the universe to expand or contract? So Einstein added an additional term. It was a correction term. And then Lemaitre talks to Einstein. He's like, no, we want expansion. We want it to expand from a single point because then you have a starting point. And Einstein listens to the reason here and is like, well, I screwed up. And funny enough, the stuff we'll learn in the next video says, no, Einstein didn't screw up. Having that parameter, having that extra term, allows for the expansion that we see today. So, it's a lot of big ideas mixing in here. But the gist of it is when you have a big bang, is that you have some initial point from which the universe evolves from, some initial beginning moment. And behind that is a principle that the universe needs to look the same at every location. So basically, the stuff starts at some point, it spreads out, it basically maintains the same density. This is the sort of thing is, if you're on Earth and you go 300 miles straight up, you're in space. The universe doesn't look the same on that scale. We are talking about groups of galaxies. The very large scale structure is lots and lots and lots of groups of galaxies. And no matter where you look, you see lots and lots of groups of galaxies. It does look the same basically in every direction. Now, the steady state universe increases that. It says, yeah, it looks the same everywhere. Doesn't necessarily have to, but yeah, it looks the same everywhere and it doesn't evolve. It will always look the same. Now, that poses a little bit of a problem is the universe is measurable, it expands. And so to fix this theory, the proponents of it said, well, maybe there's a mechanism that produces new matter, produces new galaxies to fill in the space kind of in the middle that would be empty as everything drifted away. And so you could maintain the density of the universe. And so it looks constant. And basically, trying to fix the steady state universe gets more and more complicated in the sense of what we can see now. And the simplest explanation, it's almost certainly the Big Bang. Is that there's some moment where everything exists and the laws of physics are set at that point and it evolves from there. And so that's what we're going to look at. Now, if you want to, you can research the other ideas. I gave you some names of people who were big in that and, places you can look, you can go through, but we're kind of just saying, hey, it was here, but don't worry about it. That's a lot of time on this slide. Anyway, so this is our evidence. One is we've seen the radiation left over from the Big Bang, and once we apply physics as close as we can to the Big Bang, it the evolution of the universe from those early moments gives us the correct balance of material that we see. We see the right proportions of hydrogen and helium and other elements. And so we're going to talk about these, right? And that image at the very beginning is that leftover radiation, which is not these guys. I don't know which is which. If I had to guess, Penzias is here, Wilson is here. This uh, strapping uh, person with a massive beard, I assume is the grad student, and the more mature gentleman is probably the peer instructor or the primary investigator. That's the word, primary investigator. It's been years since I've been in school. Anyway, these guys are Penzias and Wilson, and behind them is this big antenna. They worked for Bell Labs, and what they were looking for was pretty particular, but they found some just background. And ultimately, they'll end up proving or showing that that's probably from the Big Bang. Right. But what they were doing, they were building systems for Bell Lab, for the telephone company, essentially. And what they were doing was just trying to measure radio reflections from satellites. The idea is you send up a balloon and it stays above a point for a while and does satellite like stuff, transmits and receives signals. And they wanted to see the reflection, so they had an antenna, and the antenna picks up this background. They had to get rid of all the other signals. So you could get signals that have reflected off the moon and come back. You could get signals that, uh, like the planet, like Jupiter radiates, and so you could pick radio waves up from Jupiter. And so, I know there's also the Soviets were doing weird radar stuff because it's the Cold War and the Americans were doing the same thing. And there were lots of sources of background radiation, and they had to get rid of all of it, or at least identify it so that they could cancel it out. So eventually they find uh, this background noise, this hiss. They can't get rid of it. They even had a theory that pigeons lived in the antenna, and the poop was damaging the antenna, or the heat from the poop was uh, getting into the signal. So they cleaned their antenna out and kicked the pigeons out. They can't figure out what this is, and they can't explain it. Now, up the road from them, their contemporaries um, are looking for the echo from the Big Bang. They've decided, hey, there's a Big Bang is possible. We should be able to confirm it by finding this echo. They predicted this background radiation, and they were building the equipment. They're building the experiment to find it. And Bass and Wilson call them up. And because they're building this equipment and because they're researchers, these guys basically engineers for Bell Lab, uh, you know, not the Bell Labs did research, but they call up these researchers and they have a back and forth. It's like the researchers are like, well, uh where is it? And it's like, oh, it's everywhere in the sky. And the researcher like, well, how energetic is it? And it's like, well, it seems like if it was a heat source, it'd be something around 3 Kelvin. And that seems a little weird to us. And the researcher like, well, did you clean it out? It's like, yeah, we kicked 4 or 5 pigeons out of it. And they go back and forth in this discussion. And someone in the groups is like, well, you guys have probably won a Nobel Prize from this, and we can stop doing what we were doing. And they talk about it, and they realize that they've discovered this echo that the previous. Well, this is the antenna that they used. There's building here. It's up on stilts. You put your receiver here, and the signal comes in and is funneled in essentially. And it can rotate on this wheel so that you can go horizon to horizon, then go 360 degrees around on this platform. Radio telescopes are really weird structures to build for the ability to look everywhere. They're basically big engineering. But this is the antenna in place you that detected it. You can see there's stuff inside to clean out, or places where it's been cleaned. So, from our understanding of how the universe evolved, the echo started when the universe was about 3,000 degrees. Before that, in the earlier times, you would have radiation basically interact with nuclei and electrons that were trying to form, and it would just be uh, constantly absorbed and reemitted. And once it cooled down to about this temperature, you have neutral atoms, and the radiation is free to travel onwards. So the vast majority of it is propagated out. And so this is essentially the universe was opaque in an earlier time, about 380,000 years uh, after it's created. It's opaque, and then after that, it's transparent. Right, so that initial radiation should have been visible light and infrared, and it has cooled down to radio waves. It is basically the universe has expanded out to where the apparent temperature is very, very low. But what we see is that this is clearly from a hot object. This is what a radiation source from a hot object is, but its background temperature is only about 2.7 Kelvin. And I've uh, obviously got some text here that's a little weird. Let's see if I can get that moved. Oh dear, what's going on? These slides do some weird stuff. Um, and what's happened is the universe has expanded, and that causes a redshift to the light that we're seeing. And so it's redshifted 1,000 times, which means it went from visible light to microwaves. And so we've looked to map it, and we've made a few different maps. Um, this picture comes from what's called the Wilkinson Microwave Anisotropy Project. The idea is to see if there's a direction that the bang came from, if there was an obvious a place you could point to and say that's where it started. And there wasn't an obvious one. And this is fairly uniform. You can see some structure in it. And so there's further ways of looking for structure, but the structure isn't from where it started. It's from the fact that the early universe is has structure. It's not completely uniform in density. And so that structure shows up in the structure of the radiation. The other bit of evidence is the proportions of elements. And we talked a little bit about fusion and how you have certain ingredients. And in the Big Bang, it's going to be as hot or hotter than the core of a star. You're going to have um, hydrogen and neutrons forming helium, and you're going to have further increases. But for the most part, you have hydrogen and then you have some helium. And so, this combination of forming stuff is going to produce, you know, basically the first 3 minutes is where everything gets produced. And so later on, I want to try to tell you about that first 3 minutes. And if you go on the internet and look for the first 3 minutes of the universe, there's lots of explanations. So I think this is super interesting. But essentially, the formation of matter looks a lot like fusion. And ultimately, to to form from what we think was made in the universe, you're starting with a chunk of hydrogen and some neutrons, and you're going to end up with a bunch of hydrogen and one helium nuclei, but the helium nuclei is 4 times as massive. And so instead of being like 12 to 1 by weight, it's going to be 75-25. And when we look at sources of this early gas from very distant sources, it matches. So the background information, the background radiation is, you know, from fairly early on, 400,000 years into the universe. And, it gives you some idea of how the universe has expanded, how it's moved. It does show that we have some motion with respect to it. And it shows a sense of we probably have a certain amount of expansion of the universe, which means we have a certain amount of dark matter and dark energy, which we're going to talk about in the next chapter. So wait for the next video. And so it gives us a rough idea of also the age of the universe because of the time it takes to do this expansion. So there's some different views of, I'm showing you more images, but there's different views of how the radiation looks. Um, I need to put some text in here. Different ways of looking at it. There's a trend of observatories in Antarctica because it's a, a place with interesting qualities for looking. Um, Again, more Antarctica, in this case, weather balloons and such. Here's another one map picture of how the the basically the intensity of the light in particular locations. What you see is fairly uniform, but there are some places that are higher and some that are lower, and it's bubbly. So figuring out what's going on is kind of interesting. All right, so here, this is a graph of what we think the temperature looks like versus when in the creation, in the Big Bang, did it happen. And we're here at a very low temperature. This is completely logarithmic everywhere. The universe, as it got denser, as we play the video backwards and we go closer and closer to the Big Bang, I had a pointer here. We go closer and closer to the Big Bang. It has got to get more and more dense. It's got to get hotter and hotter and hotter. And, you know, 1 second after the Big Bang, it's the interior of a star hot. And it gets much, 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 much hotter. Right. And so at these very early instances, conditions are very weird. Physics starts to break. And there's a reason why we don't go further back, is we don't know. But in those very hot moments, you have lots of energy in the form of photons that can form electrons and positrons, anti-electrons. You have particles and antiparticles forming. And so the early universe was full of lots of particles and lots of radiation because it's very hot. So that early universe is kind of a weird time, right? Is now there's four distinct forces, right? We talked about them. There's the strong nuclear force, there's electromagnetism, there's the weak force, and there's gravity. Now, on Earth, in our research, we can kind of get to the point of simulating early moments of the Big Bang where we can see, oh, electromagnetism and the weak nuclear force are kind of the same force. We can kind of get some ideas that, yeah, those are linked. And we can theorize that the strong force should be linked in some way. So we have what's called a grand unified theory force. We link everything together. Gravity is the oddball. Gravity relies on the fact that there's a huge amount of stuff. And so we're trying to figure out if we go far enough back, is it linked up to these other forces? Right? Do the forces all unify? Is there basically one force that exists at the Big Bang? We don't know. We kind of think it probably is, but we can't create these conditions. We can get kind of there-ish on the graph. We're pretty certain that there's a combined electricity, magnetism, and weak nuclear force. Maybe there's other stuff when we don't know anything else. But if you hear popular science presenters tell you about string theory and grand unified theories, this is what they're supposed to be talking about. They don't know either. So, saying we know what the early universe looks like now. We have an idea that it was very hot and very dense early, and it got transparent at some point, and that's where the Big Bang comes from. There's some questions about how the universe. This is that first 3 minutes story. Your textbook has the chart on the left, which talks about the different eras. Um, and I found a different source, which has essentially the same information, but it's kind of, uh, one, it's organized a different way, and it's a little more readable, I think. So you can look in your book, you can look at this, but essentially, I would like to get to, essentially the first 3 minutes or so, which is when we're starting to form nuclei. So that's about here in this graph and about here in this graph. Eventually, once you get atoms, we know what happens. You have clouds of gas and dust to form galaxies, and they're spreading out. So there's a kind of a good question in all of this, which is all kind of related. Is the universe is theorized to start from essentially a mathematical point. It springs into existence. Why isn't it uniformly dense? Why is it as uniform as it is, and why is there structure? Right? Why it's like mashed potatoes. You can understand if there's a potato, well, that's what it is. There's potato and not potato. Or you can have the stuff that's made out of a box and it's perfectly smooth. It's mashed potatoes everywhere. But then you can have mashed potatoes that are a little lumpy because they're homemade. They're stuff that tastes good. And you're like, if you don't know what it is, you're like, well, why is it lumpy? Why is some of it a little more lumpier than others? And then there's the stuff that they make out of cauliflower. You don't want to know about that. But there's a lot of questions. Where does the structure come from? Why is it still fairly uniform? And why is the density of universe fairly close to the density needed to cause it to close in on itself? Right. And so this is that first 3 minutes. Hopefully, we can kind of talk about what's going on, and it leads to a couple of other questions as well. So, we go back to 10 to the minus 43 seconds. We don't know what happens before this. The idea is that basically all of physics breaks, but after this, gravity works. We have, we can do things with general relativity, and quantum mechanics mostly works. I don't know of any problems with it. But we don't know what happens before this. So this kind of represents. Imagine if you could show time on a screen, and there are pixels in the screen. This time step represents a pixelation. It's a minimum time in a sense. Why did you do that again? Don't do that. Weird. There's a minimum time here, a minimum time step in a sense. But people who think that the universe is simulated think this is an idea that this is the processor speed. Ignore that. That's not important right now. So no one knows what happens earlier than this. Physics just doesn't work. But eventually, physics starts working. So 10 to the minus 35 seconds, there's a sudden expansion and it cools down, and there's particles whizzing around everywhere and they're going really fast. They're super energetic, and there's radiation everywhere. And if things can get together, radiation breaks it apart. So there are particles. That's it. And the particles aren't that stable themselves. You're going to have quarks and leptons that we talked about, and then you're going to have hydrogen, protons and neutrons and electrons, and that's fairly much it. So in this little bit of time, 10 to the minus 32 seconds, there's, we think, a big expansion that pushes stuff away. The universe gets larger. And there's a reason we think that. That's going to be talked about a little bit later. Right? Is something has to lead the universe from the size that it formed at to the size it is now. And it doesn't match with what we're seeing. So there has to be some explanation, which also goes with why does everything look the same everywhere? Because it was all at the same place and then spread out. So there has to be some sort of inflation, and it fits here. Universe expands, a universe cools. Basically, we're talking about cooling down to the point where it looks like the interior of a star, so you can have fusion. Up to the first second, the universe is still cooling down. You now are certain of the number of particles you have, the number of protons, neutrons, electrons, the antimatter parts we now know. And this leads to a question. If we have energy and it's forming particles, the processes we know form matter and antimatter in equal amounts. You take two gamma rays, you get an electron and a positron. You take two more energetic ones, you get a proton and an antiproton. There should be an equal amount of matter and antimatter, and everything we see is made out of matter. So where did all the antimatter go? So we got all the particles that we're going to get, and in this step, basically the radiation and condenses out. Now you have low energy radiation and particles that will not decay. We need to explain at this point, where did the antimatter go? And we still can't form nuclei. That takes us a little further on. 100 seconds in, it's cooling down further. Nuclei start to become stable, and you're starting to fuse particles together. So at this time, we're going to set the proportions of the stuff that's in the early universe, and it's going to be mostly hydrogen and helium. So these nuclei that are forming are completely ionized. There's no electrons around because if it gains something, there's still enough radiation to ionize it. So baronuclei bounce around until eventually the temperature is about 3,000 Kelvin. Atoms are stable at that temperature. They can eventually pick up electrons. So you get stable atoms, and the universe turns transparent. So the remaining energy as photons, that's what forms the microwave background radiation. That's the leftovers of the Big Bang. And we go on from there. 4 million years in yet, the universe is just clouds of gas and dust. And then from there, we start forming galaxies and start forming stars. The universe continues to cool and expand. That's the history of the universe. So, some more images. This is what the time would look like when the first stars were forming. Kind of just big glowing areas. Looking at some of the very first stars, these are pretty pictures. Here we're seeing some of the very earliest galaxies that are forming in this uh, what looks like the Hubble Deep Field image or something like it. There's areas where galaxies are forming. And then after all this expansion and stuff, there is so all these labels are based on the constellation we can see them in or who is discovering them. But this gives you an idea of the large scale structure of the universe based on our viewing position. And there is some structure. Kind of looks wispy and filamenty, but everywhere you look, it looks like that. So, where does that structure come from? And why does it still look pretty uniform? All of that we think comes from inflation in the early universe. That little bit of time when the universe inflated suddenly. So we think that at the very beginning were very small changes in density, very small ripples in density. If there's a sudden inflation event, then suddenly the more dense areas get suddenly large and the less dense areas get suddenly large. And things are further and further apart. And you go from very tiny ripples in the background to big lumpiness in the universe. And so we think that's what gives you the structure is at the very beginning it wasn't uniform, but it was very small changes that now if we saw those sort of small changes we wouldn't be able to measure them. So another view of basically a timeline of the Big Bang. Um, you know, there's lots of these maps in your text and such. So why does the background look the same everywhere? It's because the stuff is essentially from the light is coming from places that were at the same temperature because they were at the same place at one point, right? We're looking at this, and these places are at the same temperature because we see the same radiation, but they're huge distances away when we see that radiation. But it's because they were really right next to each other, and then there was sudden inflation, push them apart. This is like taking two ice cubes. There, you know that they're frozen. They're at 0 degrees C, and you separate them by 100 miles. If they're still ice, you still know their temperature. So this gives us an idea of the universe expanding. Now, there is a little bit more going on here. The universe has some shape to it. We talked about um, how the shape of space, how the curvature of space is based on the amount of matter in it. But we can look at the large scale curvature of the universe, and we think it's pretty flat. And it kind of matters if there's just a little bit more than a critical amount of density, the universe will be a closed spherical shape, and if it's a little bit less, it'll be saddle shaped and it'll be open. We think it's fairly flat. It's probably either flat or saddle shaped, but it's really, really, really close to flat. So inflation helps with that too. If we start with the early universe, it could be strongly, strongly curved because all the stuff is all in one spot. But as the universe expands, that curvature gets smaller and smaller and smaller and smaller, like a balloon inflating. That's why it's called inflation. The balloon inflates, and suddenly the surface looks flat. So I'm kind of wondering if it actually occurs or if this is just something we need because we don't understand what happened. Or that's one of the things in all of these theories is we kind of have to constantly ask ourselves, is this really the way it happened, or can we come up with something simpler or a better explanation that fits better? So, did it really occur? Well, this graph kind of it looks at if I pick a point in the sky and then I pick a point further, at some distance away. So this is looking at the how far we move when we look at a different point, and this looks at the fluctuations. And what we see is that when points are really close together, they're fairly uniform in temperature. When they're fairly far away, they're fairly uniform in temperature. But there's a sweet spot where you have fairly drastic changes on the order of only about 1 degree of distance. And so that kind of shows us the lumpiness of that background. You see where what the structure looked like in the early universe. Excuse me. So it's kind of a weird. So what I was saying is, if I pick this point and then I pick a point over here, that's several degrees away. If I pick this point and then a point right beside it, a pixel away, that's a very small angle. And so looking at this structure, it fits the sort of predicted structure we'd get from inflation. And what we expect is the universe looks flat. The stuff we can see is about 4% of the total matter. And then the stuff we can't see makes up the remainder, right? Dark matter is about 23%, and dark energy is about 73%. And this is assuming that our age of the universe is about 13, 14 billion years. So we can infer the properties that we actually see in the universe that seem to make sense. Though we're going to have to get into the next chapter to talk about dark matter, dark energy. So just understand this is out of order for a moment. And so there's lots of explanations of what we see. There's almost zero heavy elements. There's not that many neutrinos. Stars and gaseous clouds are going to make up most of the visible matter. And then there's going to be the stuff we can't see that makes up the vast majority of it. And so there's certain regions of there's certain time steps, certain epochs of time where the universe is vastly different. When radiation is dominant, basically everything is photons. Now we're in sort of matter dominant. There's lots of atoms, lots of molecules, and then there's when inflation happens, and we kind of think it describes now as well, is where most of what's out there is stuff we can't see. So more space, that's pretty. More space is pretty. Places in green circles are places of the very, very, very first galaxies that we can see, the earliest galaxies we can see. And you notice they're almost all red dots. Now, what do we mean by dark? Well, when we're talking about these epochs, if we saw the universe when it was photon dominant, it'd glow like the surface of the sun. Like everywhere would be that bright. And in the early universe, stars would be fairly closer together and it'd be brighter. Now, when we look somewhere in the sky, we can find dark spots. You can ask a really kind of interesting question. So there's this guy called Olbert who posed kind of this interesting paradox. The idea is that the universe is infinite, the universe is unchanging, and it's everywhere the same. That means that we expect to see stars everywhere, which means that if we look in some direction, eventually we ought to see a star in that direction. But we can pick a point in this image that doesn't seem to have a star, say right there. We can imagine we should be able to find a star there. And that's true for any dark spot. The sky, if it were truly unchanging and truly infinite, and it were the same everywhere, would have to be full of sources of light. It would have to be massively, massively bright. So that can't completely be true. And the Big Bang says no, it is changing. And it might be infinite, but the finite universe, we can only see so far because the light takes time to get to us. And so we're not sure that one's true and two isn't true. So the sky is dark for a good reason. The night sky is dark because the universe changes. These images with the trees is the idea is that the picture on the right is, if you replace trees with stars, that's what we see. There's places where there are no trees. But, if you imagine a dense forest, there's trees everywhere. No matter where you look, you should see a tree. So, right, this is, you know, this basically concludes the bit I wanted to talk about here. How did we get to today? We have an instant where everything pops into creation and it's almost completely energy and photons. Particles form, and eventually the universe becomes transparent. The particles become atoms, and the light passes around. We see it, and the universe spreads out so that there's now dark areas in the sky. So the question is this going to keep expanding forever or does it contract back? What's going to happen to the universe? That's going to be the next video.